नमस्कार, मैं प्रोफेसर नरेंद्र कुमार पांडे, फिजिक्स डिपार्टमेंट, लखनऊ यूनिवर्सिटी से आज आपके सामने लेजर लेक्चर सीरीज के 12वें लेक्चर में मोड्स ऑफ अ रेक्टेंगुलर कैविटी डिस्कस करने जा रहा हूं। Now, modes of a rectangular cavity. यहाँ एक फिगर हमने दिखाया है 3 डायमेंशन में, एक्स वाई जेड प्लेन में, और ये एक रेक्टेंगुलर कैविटी है। और इस रेक्टेंगुलर कैविटी में जब इलेक्ट्रोमैग्नेटिक वेव का प्रोपेगेशन होगा तो ये दोनों वॉल्स, इससे और इसके पीछे वाले वॉल से, जो कि हम अगले पिक्चर में दिखा सकते हैं कि ये इसका पीछे वाला वॉल यहाँ पर है और साइड का वॉल ये है। तो जब इसमें इलेक्ट्रोमैग्नेटिक वेव का प्रोपेगेशन होगा तो ये दोनों वॉल से इलेक्ट्रोमैग्नेटिक वेव्स रिफ्लेक्ट होंगे और रिफ्लेक्ट टू एंड फ्रो होने के बाद वो मूव करेंगे, एंड कुछ समय तक इसी तरह से टू एंड फ्रो मूव करने के बाद में एक स्टेडी स्टेट आएगा जबकि उनका आपस का सुपरपोजिशन से एक स्टैंडिंग वेव पैटर्न फॉर्म होगा। इलेक्ट्रोमैग्नेटिक वेव का जो ये स्टैंडिंग वेव पैटर्न है, ये इसके मोड्स कहलाते हैं, मोड्स ऑफ ऑसिलेशन ऑफ द इलेक्ट्रोमैग्नेटिक फील्ड। तो इस तरह का कोई भी जो सोल्यूशन हमें चाहिए, चाहे वो स्टैंडिंग वेव सोल्यूशन हो और चाहे वो प्लेन प्रोग्रेसिव वेव सोल्यूशन हो, हम हमेशा ही इलेक्ट्रोमैग्नेटिक वेव इक्वेशन का सोल्यूशन फाइंड आउट करते हैं, उस पर स्पेशल बाउंड्री कंडीशन उस प्रॉब्लम का अप्लाई करते हैं, तो फिर हमें सोल्यूशन निकल के आता है। तो यहाँ का भी अगर हमको स्टैंडिंग वेव पैटर्न या मोड्स ऑफ ऑसिलेशन फाइंड आउट करना है तो हमें इस वेव इक्वेशन को सॉल्व करना पड़ेगा। यानी मोड का मतलब है कि डिस्ट्रीब्यूशन ऑफ इलेक्ट्रिक एंड मैग्नेटिक फील्ड्स परपेंडिकुलर टू द डायरेक्शन ऑफ प्रोपेगेशन, वही मोड्स होते हैं। सो वी विल हैव टू फाइंड आउट द सॉल्यूशन ऑफ दिस वेव इक्वेशन अकॉर्डिंग टू द बाउंड्री कंडीशन ऑफ दिस प्रॉब्लम, and we have the assumption in the form of boundary condition, that is, walls of the cavity are perfectly conducting. What does it mean? अगर इसके walls conducting हैं, इस सारे के सारे walls conducting हैं, तो naturally tangential components of electric field should vanish at the walls. इसका मतलब क्या हुआ कि E cross n is equal to 0, where n is a unit vector normal to the wall surface. So we have to solve this one to get the standing wave pattern or the modes of oscillation in this rectangular cavity. Now, generally the time dependent simple solution of equation 1 is always taken of the form e to the power of I omega t. Here omega is the angular frequency of the wave. Now we need to find out the Cartesian components as solution of the wave equation. Now each Cartesian component of equation 1 will be shown to be a linear combination of sine and cosine functions. Like if we take the x component as solution of the wave equation, then in general we can write down Ex is equal to a1 sine kxx plus b1 cos kxx, a2 sine kyy plus b2 cos kyy, a3 sine kzz plus b3 cos kzz, and of course e to the power of I omega t. Here k is the propagation vector and k square is equal to kx square plus ky square plus kz square. Now Ex is the tangential component. Now mind it, if we try to see y is equal to 0 and y is equal to 2b plane, y is equal to, this is the y direction, so y is equal to 0 is here, so y is equal to 0 plane is this plane. This plane is y is equal to 0 and this plane is y is equal to 2b. Similarly, z is equal to 0 plane in the direction of z is this one and z is equal to d plane is this one. So what do we have? In a very simple way we can say that Ex is a tangential component on these planes like y is equal to 0, y is equal to 2b, z is equal to 0, z is equal to d. Hence, as per the assumption we have taken, Ex should vanish on these planes. Ex will vanish on these planes. Thus, what do we have? So if we put y is equal to 0, for example, z is equal to 0 in this expression. So y is equal to 0 means this term is 0. Z is equal to 0 means this term is 0. Then for y is equal to 0 and z is equal to 0, Ex should have vanished. But it will vanish only if we make b2 is equal to 0 and b3 is equal to 0. You can see over here. So Ex will vanish at these planes only if b2 is equal to 0, b3 is equal to 0. So this term will vanish and this term will vanish. So here we are left with sine kyy and sine kz z. That means the y dependence of ex will be sine function and z dependence of ex will be again a sine function. We need to find out what kind of function this will be. That is, what kind of dependence x component will have. X dependence will be of ex. So we need to find out the x dependence of ex. We know the y dependence of ex as sine function. We know the z dependence of ex as sine function. So here we can see that y is equal to 0, ex is equal to 0. So if we put y is equal to 0 over here, sine kyy, and this is sine kyy is equal to 0 at y is equal to 0 and at y is equal to 2b. So we can say sine ky into 2b is equal to 0. And because at z is equal to 0 and z is equal to d also it is 0. So sine kz d is also equal to 0. So from 5 and 6 we can see from here, if we set this one as, for example, in the y, if we put this one as sine n pi and this one as sine q pi, where n and q are 0, 1, 2, then we can say from here ky into 2b, ky into 2b is equal to n pi, therefore ky is equal to n pi by 2b. Similarly from here kz is equal to q pi by d. So in the same way, x and z dependence of ey will be sine kx and sine kxx and sine kzz. Naturally that we have seen. Now this will lead again to kx is equal to m pi by 2a, just like we have found out these two. By this condition, we can find out this kx. So now for k, we know kx, we know ky, we know kz. Now x and y dependence of ez will be sine kx, x sine kyy. So one thing is clear, that is x and y dependence of ez will be sine kx, x sine kyy, and x and z dependence of ey will be sine kxx and sine kzz. Similarly, we have seen y and z dependence of ex was sine function. Now, due to the above forms of x dependence of ey, x dependence of ey, and x dependence of ey is sine function, x dependence of ez is sine function. So delta ey delta y and delta ez delta z will vanish at x is equal to 0 and x is equal to 2a. So if at x is equal to 0 and x is equal to 2a, these two functions are vanishing, then from divergence of e is equal to 0 at these two planes, delta ex delta x will also become 0. If this be the case, x dependence of ex must be of the form cos kxx, and kx is given by equation 8. In a similar way, solutions of ey and ez may also be obtained. So what we are having, the x dependence of ex is cosine function, but y and z dependence are sine functions. Similarly, y dependence of ey is cosine function and x and z dependence are sine functions. Similarly, for ez, z dependence is cosine function and x and y dependence are sine functions. So in that way, if we want to write the solution for the modes of the modes of vibration in the cavity, if we want to write down, or the distribution of electric field perpendicular to the direction of propagation, then we can write down for ex, we have e naught x cosine kx sine kyy and sine kzz exponential I omega t. Ey is equal to e naught y sine kxx cos kyy sine kzz e to the power of I omega t, and ez is equal to e naught z sine kx x sine kyy cos kzz. You can see that the x dependence of ex is cosine, but others are sine. Y dependence of ey is cosine, others are sine. Z dependence of ez is cosine, others are sine. Now, here e naught x, e naught y, e naught z are constants. So, what are the allowed frequencies of oscillation in the cavity? Kx square is kx is known, ky is known, kz is known. So omega is equal to ck, and here k is equal to under root kx square plus ky square plus kz square. So omega is equal to c pi square root m square by 4a square, n square by 4b square plus q square by d square. Now, the field configurations given by equations 9, 10, and 11 are called modes of the cavity, and they correspond to standing wave patterns in the cavity. What do we have? If we use equation 9 to 11 and the relation divergence of E is equal to 0, E dot K is equal to 0, and of course here K is equal to Kxx plus Kyy plus Kzz, and here X, Y, Z cap are unit vectors, and E naught is equal to E naught XX, E naught YY, E naught ZZ. Since the coefficients E naught X, E naught Y, E naught Z have to satisfy equation 13, it follows that for a given mode, that is for a given value of M and Q, only two of the components of E naught can be chosen independently. Third one will automatically come up. Thus, a given mode can have two independent states of polarization. Two independent states of polarization. Let us consider an example. M is equal to 0, N is equal to 1, Q is equal to 1. If M is equal to 0, then Kx is equal to 0. Ky is equal to pi by 2b, Kz is equal to pi by d. And therefore, with M is equal to 0, N is equal to 1, Q is equal to 1, the Ey and Ez components will vanish. But Ex component will survive as Ex is equal to E naught X sine pi by 2b y sine pi by d z into e to the power of I omega t. So for a given case of M is equal to 0, N is equal to 1, Q is equal to 1, we have field distribution Ex is equal to E naught X sine pi by 2by sine pi by dz e to the power of I omega t. So Ey is equal to 0, Ez is equal to 0. Using the time dependence of the form e to the power of I omega t and expanding the sine and cosine function of mind it. What we have? We have this one as the field distribution or the mode present in the cavity. Now this is a standing wave pattern. And this standing wave pattern is formed because of the superposition of plane progressive waves. So the question is, what are the plane progressive waves that are superposing on each other, that are making superposition to give this standing wave pattern? And if we try to propose that, then that can be written as E is equal to this much, this constant and this function. Now mind it, first one is e to the power of I omega t minus kyy kzz. This is a plane progressive wave in the yz plane moving in the positive yz direction. And if you want to see it in the figure, then you can easily see we are referring to this one. This is positive y direction. This is positive z. So the first progressive wave is represented along this direction. Much in the same way, the second one. This is minus kyy. So it is a positive y direction, negative z direction. Positive y and negative z. So positive y and negative z. You can see from here that is positive y and negative z. So what we have is number 2. That is, we have this one. So this way we can understand. Similarly, this is a wave moving along, moving in the negative y direction, positive z direction, and this is a y moving in the minus y and minus z direction in that quadrant, yz plane in the negative one. So these are the 4 plane progressive waves that are superposing to give the standing wave pattern that we have got for the condition M is equal to 0, N is equal to 1, Q is equal to 1. And if we see this by a figure, then this is the first one, this is the second one, this is the third one, this is the fourth one. These 4 plane progressive waves are superposing to give that particular standing wave pattern. So a mode corresponding to M is equal to 0, N is equal to 1, Q is equal to 1 consists of 4 plane waves having directions of propagation as shown in the figure. The mutual interference of these waves produce a standing wave pattern in the cavity as we have seen. Now if neither M and Q, none of them is 0, in that case the cavity modes can be thought of as a standing wave produced due to superposition of 8 waves, 8 plane progressive waves. Now let us consider a little bit more that how many number of modes are present per unit volume in the cavity in a particular frequency interval between nu and nu plus d nu. This is a common formula. This can be seen in any textbook. Rho nu d nu is equal to 8 pi nu square by c cube d nu. If we put typical values of nu is equal to 3 into 10 to the power of 14 hertz, d nu is equal to 3 into 10 to the power of 19 hertz, rho nu d nu is equal to 2 into 10 to the power of 8 per centimeter cube. That means in a small frequency interval like this, there are approximately 10 to the power of 8 modes per centimeter cube. Mind it, each mode will be vibrating with a different frequency. That means we will never have a monochromatic radiation. We will never have a monochromatic radiation. So in a closed rectangular cavity resonator, if these are the number of modes present, we will never be able to get a monochromatic radiation. So what is the way out? The way out is that, let us see, if we remove the side walls, so mind it, if M and N are large values, then they will refer to those modes propagating far away from the propagation axis. So if we do not have the side walls, then modes having large M and N values will not be reflected back and will be lost out. So what we are going to propose is, in place of a closed cavity, if we keep an open cavity, then the values of Mn, that only those modes will be propagating which have lower value of Mn and larger value of Q. Larger value of Q will indicate as propagation as close to the axis as possible. So we are going to consider the small values of Mn and large value of Q, of course. So small values of Mn will mean we are dealing with open cavity, not a closed cavity. So if it is an open cavity, so in the first place, let us see what were the allowed frequencies in the rectangular cavity resonator. These were the allowed frequencies we have seen. So from here, we can see this omega can be written as 2 pi nu, and so nu is equal to c by 2 q square by d square plus 1 by 4 m square by a square plus n square by b square power half is equal to this much. We have taken out q by d from the bracket here, and then we have 1 plus d square by 4q square m square by a square plus n square by b square power half. Now let us see. From here, because we have considered an open cavity, so values of m and n are very small and value of q is large. This is large and these are small values. In that case, this can be expanded by binomial expansion, and therefore we can write this expression as c by 2 q by d 1 plus d square by q square multiplied by 8. Here it was 4, this half multiplied comes here, so this becomes 2 into 4, that is 8. So after binomial expansion, nu is equal to c by 2 q by d 1 plus d square by 8q square m square by a square plus n square by b square. This is what we are getting. That is this expression. So if in the open cavity we keep m and n constant, that is, we are not talking about transverse modes, different values of m and n will refer to transverse modes, and different values of q will refer to longitudinal modes. So if we are keeping m and n fixed and we are changing q is equal to 1, then the frequency will be c by 2d. Q is equal to 2, frequency will be c by 2d. Q is equal to 3, frequency will be 3c by 2d. 1c by 2d, 2c by 2d, 3c by 2d. So if we are considering only the longitudinal modes, then the separation between the two consecutive longitudinal modes will simply be, as you can see, c by 2d. That is c by 2d. You can see from here. So the separation between two consecutive longitudinal modes is c by 2d. Let us reinforce it. This corresponds to longitudinal mode spacing. Modes having different m and n are transverse modes. Modes having different q are longitudinal modes. Thank you very much for your kind attention. So these are certain references. And this is a disclaimer, thus this content is exclusively for academic purposes and no economic or commercial interest is involved. This is a YouTube link where you can find all my lectures present.